Okay, Matt Roscoe here at the University of Montana. It's a lecture on Diophantine equations, section 2-5 from our Burton text in Math 326 number theory. So I want to first tell you a little bit about the background story on Diophantus, just a few slides on the person whose namesake has been attached to a specific type of equations, which we'll then define. Those are Diophantine equations, and then we'll talk about the general solution method and do a couple examples. So one thing we know about Diophantus is he had a famous problem on his tombstone. So this is known as the Diophantus epigram or epitaph problem. It says his boyhood lasted 1/6 of his life. His beard grew after 1/12 more. After 1/7 more, he was married, and his son was born 5 years later. His son lived to half of his father's age, and the father died 4 years after his son. So maybe a fun way to give a nod to Diophantus might be to solve his epigram problem. So let's go ahead and do that now. So let's see, what do we know? If we let D be Diophantus's age at death, and if we let S be his son's age, then we know that 1/6 of his life plus 1/12 of his life plus 1/7 of his life plus 5 more years. This was sort of the length of his life without his son. So I don't know, we could say this is before the son arrives. And then the son arrives and he lives, let's see, for a certain number of years. So let's call S. And then 4 years later, Diophantus dies. So this is, I guess, the part where the two of them were alive together, so he was with his son, and if he dies, then what we can think of is that this whole thing must be equal to just D, however old Diophantus was at the age of his death. We're also given the fact that his son lived to be just half of his age at death. So in other words, if I take 1/2 of Diophantus's age at death, I would know how old the son was at death. So it looks like we have a system of 2 equations and 2 unknowns. We should be able to solve that. I think the easy way to go here would be to just substitute in for S what we know S to be here. So 1/2 D in for S up there would probably work nicely. So I would get, if I substituted equation 2 into equation 1, I get 1/6 D plus a 12th D plus a 7th D plus 5 plus, I guess, a 1/2 D plus a 4, and that must be equal to just D. Adding all of the D's, the like terms, together on the left-hand side, what you'll find is that you get 25 28ths, I think. Yeah. 25 28ths is 1/6 plus 1/12 plus 1/7 plus 1/2. And then the 2, 5 and the 4, that'll be 9. And that will equal D over here. And so we're at that stage. So 25 28ths D plus 9 is equal to D. So I would probably subtract the 25 28ths from both sides and get 9 equal to 3 28ths D, and then go ahead and solve for D by multiplying by 28 and dividing by 3. So what do we get for D? D is going to be 84 then. So that's Diophantus's age, and the sun's going to be half that, so 42. Kind of a fun problem. But what we know mostly about Diophantus is that he he leaves behind in the physical record a text called the Arithmetica, which provides evidence of the first systematic use of mathematical notation in the analysis of some 200 problems. We actually only have a part of the Arithmetica that survives. We know that it was larger than what survives based on other people's writings, but the 200 problems that do come to us in the modern era give evidence of the rise of the use of mathematical notation for the first time in the historical record. Um, the fact that most of the instruction in Arithmetica comes in the form of problems is something that continues in the historical record of mathematics. And here's one such type of example that comes to us from quite I guess 1,000 years, roughly 1,000 years forward from Diophantus. And I thought it would be a good problem to think about a little bit before we introduce what a Diophantine equation is, or I guess as a means to introduce what a Diophantine equation is. So we have this problem that says 100 bushels of grain are distributed among 100 persons in such a way that each man receives 3 bushels, each woman receives 2 bushels, and each child receives a half a bushel. How many men, women, and children are there? So kind of an interesting question. One thing you should notice before we step back and start thinking about it is that it's definitely a question of number theory because it's an integers only situation. We can't have, half a man, woman, or child. So we're trying to partition the 100 people into 3 groups in such a way that the bushels are distributed according to the rule of 3 bushels a man, 2 bushels a woman, and half a bushel a child. So let's see if we can get a sense of what this type of a situation leads to in terms of an equation. Go ahead and maximize this out again. All right, let's go back here. All right, well, if we let M be the number of men, W be the number of women, and C be the number of children, and what do we have? Well, we definitely know that the number of men plus the number of women plus the number of children has to be equal to 100. That's a count of people. Like we're given that in the problem. There's 100 people. We also know that if we take, we could count the bushels too, right? That 3 times the number of men plus 2 times the number of women plus 1/2 times the number of children has to be equal to 200, or excuse me, 100 bushels. Just to get our coefficients all in integers, let's go ahead and multiply this second equation times 2, so we get 6m plus 4w plus c is equal to 200. Again, that would be bushels. Let's go ahead and notice that on the first equation, we could, well, I guess we could sit and stand back and think a little bit. I noticed that there are 3 equations, excuse me, 2 equations, really just these 2, the top and bottom, but there are 3 unknowns, MWC, which means that there should be more, this is in a deterministic setting. We don't know exactly, we probably aren't going to be able to solve exactly for M, W, and C, but we should be able to say at least a little bit about their solution, I would think. So one way we could attack this is we could notice that I could solve for C in say this equation and plug it in for C down here to at least eliminate one of the 3 variables. So I'll do that now. I'll say that this is the same thing as 6m plus 4w plus, okay, so C here would be equal to 100 minus m minus w and that would be equal to 100 over here. Excuse me, 200 over here. Doing a little simplifying, what we'd see is 6 minus m, that would give us 5m, and 4w minus a w would give us 3w. And let's see, take 100 away from 200, and I would get 100 on this side. And so that's what we get in this particular type of equation. That results is called the Diophantine equation. It's a Diophantine linear equation, I guess, to be more specific, but the idea is that we're trying to find a linear combination of 5 and 3 such that it equals 100, and that the two, I guess, the two parameters m and w have to be found in the integers. So a Diophantine equation there, we could do a little bit of thinking about this. One way to think about this is to, well, let's just see if we can find a few examples. If we set women to be 0, for example, we'd know that men would have to be 20 right away, right? Another solution would be to say, well, what if we made 10 women? Then there'd be 30 bushels of grain distributed to them, leaving 70 bushels of grain, which divided by 5 would give us 14. So 14 men and 10 women is an example. Oh, and maybe we should even think in terms of children, right? So if there were 20 here, there'd be 80 here. If there was 10, 24 there would be 76 children here. We could do one more here, example. So what if there were 20 women? If there were 20 women, then there would be 8 men, 28, so 72. And you can see definitely some series, and it looks like they're arithmetic in the table. This one going down by 6, this one going up by 10, this one going down by 4. So some interesting number theory things going on in the solution here, which we'll explore. Well, a Diophantine equation is just this. It says if we let a, b, and c be integers and ensure that both a and b are not both 0, then the equation ax plus by equals c, whose solution xy is restricted to the integers, is called a linear Diophantine equation in 2 variables. So just a specific type of equation that has a little bit to do with some of the theory, well, has a lot to do with the theory of divisibility we've been developing. So let's take a look at these 2 Diophantine equations and just think a little bit about what observations you could make. So I'll just give you a second to think about that. So one of the things you might have thought is that the first one has solutions in the integers and the second one doesn't. The first one definitely has solutions in the integers because I can, I guess, pretty quickly identify one. For example, I could let x be equal to 2 and y be equal to 1, and then I get 8 plus 8 is 16. So definitely a solution exists in the first one. In the second one, it appears that a solution wouldn't exist in the integers. And the reason being, on the left-hand side, we have 4 times a number and 8 times a number being added together. On the right-hand side, we have 15. And so thinking in terms of evens and odds, it seems like on the left-hand side, no matter what I do, I'm going to have an even number. And on the right-hand side, I have an odd number. And that seems to disallow any solution here, at least in the integers. So it appears that certain Diophantine equations are solvable and others aren't. Another thing you might notice is that the one that does appear to be solvable might be simplifiable, so you could reduce it by to reduce its complexity by dividing both sides by 4. You might also notice that there seems to be multiple solutions. For example, the 4x plus 8y equals 16 equation, the first equation, a second solution in addition to the one we've already identified might just be 0, 2, so x is 0 and y is 2. So some interesting things to notice there. And let's go ahead and move on and think a little bit more deeply about it in the next slide. So one of the interesting things about Diophantine equations is we can predict whether or not they're solvable by looking at the GCD. And it turns out that a Diophantine equation of form ax plus by equals c admits a solution if and only if d divides c, where d is the GCD of the coefficients a and b. So maybe we should just go back a page and make sure that that's true for this first one. And I can see that it is true, right? Because the first one, the GCD of 4 and 8 is 4, and 4 divides 16. So indeed, that Diophantine equation has a solution. This is such a big theorem that we should probably construct a proof. Let's go ahead and do that now and make sure that this is absolutely true. All right. So here's our hypothesis. Diophantine equation ax plus by equals c has a solution if and only if d divides c, where d is equal to the GCD of a and b. Okay, so one thing I want to point out is that this is an if and only if proof, so we need to both show that it's necessary and sufficient, so one direction and the other. Let's go ahead and construct our proof. I'll do the one direction in one color and the second direction in the other. So let's see, let's let ax plus by equal to c. So we're going to start with this and say it has a solution and we're going to call that solution x naught, y naught. Okay, so x naught, y naught into this equation produces this true statement. So what does that mean? That means that a x naught plus b y naught has to be equal to c. We'll call that equation 1. Okay, so then we'll let d be equal to the GCD of a and b, right? Then what can we say? Well, we can say that a is equal to some dr and b is equal to some ds for some r and s in the integers. So keep in mind that d being a common divisor of a and b means that I can find some multiple of d that's equal to a and some multiple of d that's equal to b. That's all this is saying here, right? So what are we going to do here? Does everybody see that now we have some substitutions we can make? I hope you can see that. And, this a could go in for that a, and this b could go in for that b. And if we do that, what do we get? So let's see, let me just say substituting, what are we going to get? Let's see, so if I substitute in there, where do I want to put this? I guess I'll go underneath. What do we get? Let's see, so instead of ax plus by, we get dr for A times x0 plus ds for B times y0 or y0, which I notice right away has a common factor of d, so I'll factor out d. I get r x0 plus s y0 equals c, and so that seems to imply then that d divides c, because d times some integer is equal to c. Okay, so in other words, we've shown the first part of the theorem. Remind you that what we're looking at is this equation has a solution if and only if d divides c, where d is the GCD. So we've shown when this has a solution, d divides c. So d, the GCD of A and B, d divides c. Okay, so we've shown it one direction. Maybe I should put as desired. Okay, so now let's switch directions. So now for the converse, what are we going to do? We have to start with just the opposite, so let me bring it back. We have to let d divide c and show that the Diophantine equation has a solution. Okay, so let's see. Let's let d be equal to the GCD of A and B, and let I need to switch my notes. D divides c. So then what can we say? Well, if d divides c, then c can be written as some multiple of d, right? So let's call it dt for some t in the integers, correct? Okay, well, now, since we can always find a linear combination of A and B equal to the GCD of A and B, we know that what? Well, we know that A times some x1 plus B times some y1 has to, you can always find an x1, y1 such that the linear combination of A and B is equal to D, the GCD. So that's from a previous theorem in our course. I should probably say what x1 and y1 are. So for some x1 and y1 in the integers. So let's see, we've got this. It's not, what we want to show is that there is some solution where it's equal to c, but this is where things get kind of fun. If we multiply both sides by t, what do we get? What do we get? We get, let's see, where do I want to put the t? I'm going to put it in the middle. ATX1 plus BTY1 equals DT. But going back to sort of where we were, you know, C times C is equal to DT. So this is actually C itself. And factoring out the A, I could call this A times TX1 plus B times TY1 equals C. And we can conclude, so the Diophantine equation AX plus BY equals C has solutions what x would be tx1 and y would be equal to ty1 as desired. And that's it, right? So we found a solution assuming that that D divides C. So when D divides C, there is some solution that we can find. It's this, a solution. And so we've shown the converse. All right, so that concludes the proof there. So we've proved that a Diophantine equation of form ax plus by equals c emits a solution if and only if the GCD of a and b divides c. Let's take a look at the next screen here and think a little bit about this. How would we solve this, and is there some general solution method? So let's go ahead and delve a little deeper into the Diophantine equation that we have right there and think a little bit about. I'll make this bigger this time. So let's see, what do we have here? We have something of the form 4x plus 8y is equal to c, is equal to 16. So this is, we had a few solutions just by looking at it. The first thing you should notice is that the GCD of 4 and 8 is indeed 4, and 4 divides 16, so there are solutions. We could find a few x, y. We found this one before, 2 comma 1, right? And we also found this one, 4 comma 0. It does appear if I made this one 6, then I'd have 24, and I'd have to subtract 8 to get 16, so negative 1. If I made this 8, I'd have 32, and I would have to subtract 16, so negative 2. 10, negative 3, it looks like 12, negative 4. So there is some sort of partner pairing that goes on here. So we could kind of think of the solutions as, let's make some room, as starting with a certain solution and changing. So let's say it starts with 2 and it starts with 1, and then each time I get to a next solution, I have to add 2 here times some integer, right? So add 2 a certain number of times. So I'll let t be the number of times and say add 2 for a certain number of t's. And each time I add 2 to the x solution, I have to subtract 2 from the y solution. So I could say this is the same thing as negative 1, or I guess minus 1t here. So it appears that this would be a set of all the solutions for x and all the solutions for y. And so how would we generalize this? So we could generalize this by saying I start with some x0 and I add some number, a certain number of times, and I could start with some y naught, and then I subtract a certain number of times, right? And the question is what goes in these two boxes? I think it seems intuitive that we could start at some spot, and if I increase x, I'm going to have to decrease y. One thing I want to just draw your attention to, that it turns out that this number is 2, and it should be somehow dictated by, what a, b, and c are. And one potential guess might be that you start this one by taking the 8 and dividing it by 4. And you do this one by taking a 4 and dividing by 4. And where are those numbers coming from? Well, the 8 appears to come from B, the 4 appears to come from A, and then what would 4 be? And 4, I'm pretty sure, well, you might guess it's coming from A, but another good guess might be that it's actually the GCD of 4 and 8. So So one potential guess here might be, and maybe it would be a long shot, would be that the general solution is x naught plus b over dt, and the general solution here might be y naught, minus a over dt. And we'll go ahead and draw this half of the video to close right there with a guess on a general solution, and we'll watch the next one to see if we're actually right.